Welcome to the solstice edition of Demystifying Science. We have with us today Mr. Forrest Bishop, and Forrest came to our attention because he is a natural philosopher of the classical tradition, and he wrote a series of blog posts called The Pleistocene Murders, which ask and answer the question, why did the megafauna of the planet all seem to go extinct around the time of the last ice age, despite the fact that they had survived previous glaciation periods? And he went through the records, he connected a bunch of biological, archaeological, and geological pieces, and came up with quite an interesting story that he's here to tell us about. So, welcome, Mr. Forrest Bishop.
Thank you, Shiloh and Anastasia.
Anastasia, yeah. That's a little harder one. So,
Anastasia.
indeed.
Do you like Shiloh or Michael or Dr.
Yeah, those are all 3 degrees of formality. So I
Dr.
don't know how
Hot
well
Ice?
we know each other, but you know. You can call me Michael Shiloh. You can call me Dr. Michael Shiloh DeLay if it pleases you.
Ease into it.
Man, I feel like I should have like a daytime TV show with that kind of a name. But. All right, dude. Yeah, tell us about it. Why'd you get into this? This is. I love your blog. It absolutely was one of the most beautiful pieces of theory that I've read in recent times. Especially, you know, you're not coming out of the academy, which is kind of cool. And yeah, I just thought it was a really transformative read. And you know, I know, totally outside of the scientific realm, but I loved how it culminated in this sort of purposeful place for human beings, which is great because, you know, in this super automated virtual universe, it's kind of, it's tricky to see people valuing purpose. And so I dug that a lot. But yeah, man, tell us how you got into this.
Yeah, and that is, of course, a bold claim, but then so is the claim that humans are a cancer on the planet and evil things. So this is kind of a counter argument to that as well. How I got into it is I study lots of different fields, and I've always been interested in the big animals of the past. As we all, you had the little plastic dinosaurs, right? When you were kids.
Yeah, big animals are crazy.
You had those, right? The little plastic dinosaur sets.
Absolutely.
Yeah, and so you know, these huge, just wondrous animals that we never got to see because they all died right before we showed up. It's like, oh man.
especially the big furry ones, from what I understand, right? It was there was basically giant, oversized versions of all of our favorite, you know, big ranging animals. Like the buffalo were twice as big.
Armadillo.
And, you know, there was furry elephants everywhere.
Different kinds of elephants.
Until very recently, right? This was like 12,000. Very recently.
12,000 peer-reviewed years ago. And what I mean by that is nobody really knows, you know, the datings of these things, how long ago it was. Some people think it was much more recent. And I did put a line in there in one of the parts about, and the comet hit, and it hit the Canadian ice cap, vaporized it. Part of the water went into the upper atmosphere, enough to make rain for, say, 40 days and nights.
That sounds very biblical.
What I'm saying there is that we may have a collective cultural memory of that event, which is supposed to be 11,800 years ago, but it's hard to see how a story like that could be carried on for so many thousands of years. So that's a bid for moving that date forward. But in the end, it doesn't really matter. The dating doesn't matter. It's the sequence of events,
right?
That I'm painting this picture, and of course, I'm cherry picking and being selective. So this isn't. We never know the full truth. It's never 100%. We can never be certain of everything about something that's so elaborate and so far in the past.
Right.
And putting things together into this picture that look like they fit with near certitude, but as good as we can ever be. We're finite mortal beings. Here we are. But how?
Right on.
So I've looked at that too because it is such a mystery, and over the years, ponder those questions like we do the different things. You guys do all the different things. A little bit on this, a little bit on that, and maybe 10 years ago, I came up with this idea that Earth's gravity had increased a little bit.
Well, there's another theory in that direction that we were curious about, which we haven't actually been able to get access to the guy. But because I saw in the blog that you mentioned it a couple of times.
Expanding.
Is the thick atmosphere theory, which is the fact that like the Earth's atmosphere has become less dense, and so it would appear that gravity has increased, but in reality, the atmosphere has just become less buoyant.
That one doesn't work.
Interesting. How come?
It doesn't work for numerous physical reasons. Okay. You can make the atmosphere thicker, but to get it to the thickness that a thing like a brachiosaur or even a T-Rex could use the buoyancy force to counter the gravity, it would have to be as dense as water. I mean,
that's the argument. Yeah.
Yes, it is.
It's a pretty good page, actually. I recommend it. It's like this guy's name is David Esker. I think he wrote it while he was at university. I've
read it long ago. There's another guy that thinks the Earth used to be oblong so that the gravity was less, and it was like egg shaped. And there's all these different theories about how these dinosaurs could exist, which is off topic for what we're talking about. So I waved at it a couple times. But I said giant dinosaurs eating the giant leaves, but I didn't say why because it's too far off topic for.
Well, I think that it links into the story because I think that the story is the idea that the Earth changes dramatically and these are massive shifts and there's a lot that we don't know about the past, and the stories that we tell are in many ways incomplete as a mechanism for being able to give a full explanation.
Yes, absolutely. We just have. We're trying to look at this vast panoply, this panorama of the past, and always it's like a pointillist picture with not very many points.
Yeah, exactly. You're like, you have 10 points. Connect them as any way that you wish.
And honestly, that's why science is a work in progress at all times, because as soon as you get a few more points, things look a little differently.
In fact, I can see it right behind you in your background picture. There's just some points.
Yeah, exactly.
What is spaceship isn't. It's just a picture out the window of the spaceship.
Oh, okay, cool. Right on. Anyway, yeah.
So basically, the theory was constructed because you started looking into the past. You started realizing that there are pieces that are not necessarily explained or explained in ways that you don't necessarily think.
And other people have tried. It's been called the Fermat's last theorem of paleobiology.
I mean, I want to add. Can I just add one thing that it's very, very strange because there was several of these. There's dozens of these glaciation periods, and the animals survived through them just fine. And then all of a sudden, in this last one, the animals disappear. This is what makes it so very bizarre, and it can't totally be blamed on humans because if I understand it correctly, the Australian hominids coexisted with the large megafauna for something like 30,000 years before that, before this extinction event. So what's going on? You can't blame it on the humans. You can't blame it on the climate. I mean, at least the cycling of cold and hot. So that's what I just wanted to recontextualize how wild it is that all of a sudden they just disappeared 12,000 or whatever, however many years ago.
Yeah, and when you say dozens, that's a point of contention too. First, there was one ice age in the 19th century, and then there was two, and then there was four. So right now, there's just like they keep changing the periods of when was the Pleistocene? It used to be 5 million years, now it's 2.8.
Totally.
Everything it's always in a state of flux because.
Well, this is only 150 years old. Like the first time they even thought of an ice age was like 150 years ago, I think. Like these people started looking at these moraine fields and were just like, and I think their ancestors had been telling them that these were from some sort of ice period, and everybody just wrote it off as like, it's just like folktale sort of thing.
Okay.
And so recently, this became actually a sort of academic idea, like very, very. It got some got suit and pants, like it got a nice dress.
What you said is an interesting memory. I was talking about Noah's the flood stories, which are worldwide. All the cultures have a flood story, and a lot of them are very similar. Where one man and a woman they land on this log and they float along and they restart the whole culture.
I mean, the flood stories really make sense because you're located in the Pacific Northwest, so are we, and the sort of the central story of the Pacific Northwest is the Missoula floods. And this is a story that was completely not accepted by academic geologists for a really long time until J. Harold Bretz, or I think J. Harlan Bretz, he basically came through and he on the 30s, like on foot, traced the landscape and was like
board and scab lands.
Yeah, exactly.
And all these astonishing things. But I didn't know that the Indians had that. You're saying that the Indians had that in their legends of the flood? They had a flood?
I mean, I think.
Well, I was talking about the Northern European indigenous people, actually. Like they basically all had. They were telling people. I don't want to say exactly where, but I want to say it was in the Alps or that might. What were the mountain ranges in Norway as well? I'm not too familiar with the geography there, but those people had been telling the city people for hundreds of years that there was the glaciers basically that caused the moraine fields, that caused these big polished boulders to show up. And all of the people, the academics in town were just like, "You're crazy. Those are formed by droplets of lava or something like that." And so,
fantastic.
That's
another bid for a more recent happening than 11,008, because how can a legend like that pass down through so many thousands of years? But
I guess that's what song and story are for. I mean, there's
like, I mean, it makes sense to me that you would be in a place and your family and all the way back has always been in this place, and there's always somebody who asks the question of like, hey, how'd that get there? And you're like, well, somebody once told me that it was like this. And because I think that the question of how did this come to be this way is a really, really human question in a way that I don't see my cat asking the question of how did things come to be this way. And so I doubt that the cats would have generational oral history. Maybe they do. I don't know. But it does seem like a human thing to be always asking the question. And the thing that makes science so interesting is the fact that we're attempting to be like, well, what is a robust answer to that question?
Counter argument.
And
yeah,
when you rest, all right, is that yes to everything you say, and especially when you have an isolated group, so they're not distracted by this and that and the other and forget their core culture. But there's the game of telephone problem, there's the broken link problem. Game of telephone, you go around the ring, and by the time the original message, by the time it gets back, it's something completely different as you're telling it from one person to the next. That's one problem. But for a simple story, there used to be ice here. It's a clean message, so it's not extremely susceptible to the telephone problem, but it is still. And the other problem is the broken link, which is it only takes one generation to forget the story and not pass it on.
But generations aren't isolated. There's always overlap, right? There's going to be, different ages of people, and
there's going to be some crazy old woman who lives in the mountains, or some hermit that lives in the forest, and they'll be the ones that are the keepers, and someone seeks them out. And
we did a deep dive on this. Actually, we made a movie about it at our YouTube channel. The idea of cultural transmission of knowledge is a whole other can of worms. But if anybody wants to check that out, we did do a movie on it, and it's at our Demystifying Science YouTube show. Yeah.
Okay.
But anyways, back to the actual story for what caused it and why. And why is the sort of fun part, but what caused it? What do you think? Maybe you can just outline the theory for everybody real quick before we even get into the.
Okay. Yeah. Okay. What the heck are we talking about? Okay.
Yep.
Yeah.
Yeah. All these big animals, they died in the ice age, and nobody could figure out why. And we've known about it for maybe 2 centuries or less, about the ice age and about all these massive animals. And a lot of different people have looked at and tried to solve this mystery. It doesn't make sense why all these beautiful creatures just up and croaked one day. So it's come down to two major competing theories. One is that the climate change because of the ice and the cold and the dry weather, and that's one theory. There's two main theories. The other one is that humans killed them all off.
And there's problems with both of these ideas.
Massive problems, especially with the human hunting theory. It's just physically impossible. Our ancestors were little tribes dotted here and there, running around, and these. You have to appreciate the scale of this event. This wasn't just a little endangered species here and a rainforest there. It wasn't like that. It was these animals owned this planet. Their combined mass was possibly more than the combined mass of all humans and all of their livestock put together. It was most of the animal mass on the planet of the large animals. That statement I'll have to check, but it was something like that. It was enormous how much animal biomass disappeared, just went poof over the span of a very short time, geologically speaking. And again, our dating and timing is, we don't really know when.
Well, it's also like there are plenty of animals, right? There's plenty of animals, a lot of animals, herds of buffalo. Like, it's not that animals as a whole, like humans didn't eat everything in sight. Like, for some reason, it was the large ones specifically that disappeared. And the humans overlapped with them for many years. There's been many glaciation periods. Like, these are very unsatisfying answers.
Yeah. Now, these previous glaciations, previous ice ages, the four main ones are the last one, 12,000 years ago, 18,000. One before that, about 120,000. One before that, about 120,000. So at the current thinking at the moment is they were kind of evenly spaced every 120,000 years. And there was four main ones, but then other people have been adding a lot of little ones, which we don't really need to go into. But the interesting thing is that during those three previous main ice ages, which span
so I gotta clarify something really quickly. So the word ice age is different than glacial period, right? So an ice age consists of a bunch of different glacial periods, and the last glacial period ended about 15,000 years ago, and it looks like the glacial periods happen. I'll get back to you on that, but the ice ages are these bigger chunks of several glacial periods, which is kind of confusing. Okay, anyways, go ahead.
Okay, I'm glad you said that, because I'm using ice age because it's colloquial and people know what that means.
Right, and I think Anastasia did when she introduced you.
I didn't think it had a more rigorous meaning and go into definitional lawyering about what we're talking about. So
we're all about definitions here, so there will be lawyering.
Well, it's really confusing. This threw me off too when I was a kid, because I didn't realize there had been so many of these, right? And like the fact it's often thrown around like, oh, we're actually living in an ice age right now, which is true by definition. And it's like, it doesn't feel like it's an ice age, and everybody's like, it's global warming. And it's like, well, the Earth's been through some crazy stuff. So this is just the most recent rendition, is we have periodic glacial and interglacial periods.
Yeah, I can see where the confusion, because different people use the term to mean different things.
Right. So what you're talking about, the last interglacial period was actually 194,000 years ago and ended 135,000 years ago. Yeah. And then there's this one that ended about 25,000 years. Ended about 15,000 years ago. So that's the most recent one.
Or 12 or 11.8 or 8,400. Different people.
So yeah, about every 100,000 years. Gotcha.
Roughly, and four of them during the age of the current definition of the Pleistocene, which also keeps changing. So
right,
shifting definitions. I land on ice age because everybody knows that term. Non-scientists, people that watch movies and things.
Yeah, definitely.
It means the continents were covered with ice, and there was these giant woolly mammoths running around.
Yep.
That's why I'm trying to talk as far as I can to the common man this is not his field. So I don't use terms like, what was that period?
Glaciation period.
I think it's just glacial period.
Oh,
actually.
sorry, glacial period.
Not only is he about definitions, but he doesn't even use
I
them
screwed
correctly.
it up too.
All right. So basically, okay. So we have this ice age that, and I think this is called what, the Younger Dryas ice age, which is the one that ended about 15,000 years ago.
Younger Dryas is more like 9,000. I think that was a redux, a slight repeat of the ice age that had already ended. It was starting to warm.
Interesting.
It got cooler for a little bit, and then it continued to warm. So
I see.
It's like a little blip.
bringing those things in too. Here's the thing: the problem with this problem, the interesting fact about this topic we're on, is that there are so many aspects to it, and different. Like you rattle off a bunch of fields, geology and this and that and the other, and it's so easy to go down all these other paths and add and add and add and add, and so trying to just strip it down to the really things that count is what I was focused on in this essay. Everything is, the pieces are pretty short, but everything in them builds to to the theory. There's a reason for everything in there. And so
right.
Well, we could talk about, this little thing over here.
Well, can you just summarize the theory for everybody, just so?
Okay, so the theory is, and that the Earth has been getting colder, and the Pleistocene marks the beginning of the ice ages. Ice ages, or you could call the Pleistocene the ice age, but it's been up and down. It'll freeze for thousands of years, and huge glaciers, ice caps cover the continents, and with which Antarctica is still like that now. But the ice sheets used to go all the way down to pretty much Seattle and all of Europe, most of Europe, and there were massive, massive ice sheets. All of Canada was an ice sheet, and then it'll recede, and the Earth will warm up. Well, and it's happened 4 times in the last, I don't know, 1 million years. Say, doesn't matter. And during the first 3, there were animals that went extinct, big animals that went extinct, but not very many. It was a little bit here and a little bit there. So all of these, the megafauna, the big animals, they didn't all go extinct in this last ice age, but I'd say 95% of them did.
Which is kind of a crazy thing, right? Because it's like, why?
But the other 5% that went extinct before, they were almost like the leaders, if you will, into the grave. So there were other big animals, successful animals, been around for millions of years, that went extinct in the 3 prior ice ages. So they're like the precursors. So they're telling us that yes, there were conditions that were almost bad enough, almost bad enough, almost bad enough, and then absolute disaster.
So is there something about those the ones that went extinct first, that you can sort of that differentiates them from the 95%, or?
Boy, that's a great question. I wish I haven't.
All right. Well,
Let's hear the theory, though. I want to hear the theory. Like, let's get the theory out, like summarized on the table.
Okay, so the theory is that, in addition to the fact that the massive ice caps, the carbon dioxide level of the Earth's atmosphere has been decreasing throughout the entire history of the Earth. That we pretty much know. And it wasn't until the Cambrian that the CO2 level came down. It has to be below about 5 to 10,000 parts per million before an animal can breathe it. Otherwise, they suffocate. Yeah, that's why there couldn't be land life during the Cambrian, because the atmosphere was unbreathable for animals. Even though it had oxygen.
This was like a billion. This is like 1.5 billion years ago, like really, really long time ago.
Cambrian?
5.5. Yeah, a billion years.
560.
It was a suffocating atmosphere.
Million.
560 million years ago.
Millions. Okay.
Starting of the Cambrian. Again, these are all peer-reviewed years. I
long time ago.
hasten to remind you, each one of them. So that's just something I slipped in there. A little snark.
So what happened?
When it was. So the point is, we do know that the Earth used to have a lot, like 10% of the atmosphere, and it's been falling ever since, with ups and downs. So by the time we got to the Pleistocene, the ice ages, it had dropped down to maybe 300 ppm. But then during all 3 of those ice ages, the carbon dioxide level dropped down even further.
So it's interesting because, like, if you're looking at the Cambrian, it looks like the sort of the peer-reviewed numbers, the fact that there's about 4,000 ppm during the Cambrian, down to about 180 parts per million during the Quaternary glaciation.
Yes.
And that was in the last 2 million years, though. But we're talking about, like, so the transition that we're talking about here is an even later transition, and so there's been low carbon dioxide concentrations basically for the last 2 million-ish years, right? Because if you go all the way back to the dinosaurs, you have this sort of tropical earth, ginkgo growing in the Arctic, crazy things.
Crazy, giant trees and all that, yeah.
Right. And so, but there is something that happens during the last glaciation where the creatures die off, but is it
selectively too? The selectivity is what makes it so intriguing.
Right.
It's just certain ones that were most vulnerable. And as I mentioned in the paper, it's like you'd think when it gets cold, the biggest animals would have the best chance to survive because, surface to volume, ratio.
Yeah.
It was the biggest animals were the most vulnerable. So it could have just been the cold itself. So, but during each of those four, we'll just talk about the four main ice ages or glaciation events of the past million years.
It's actually been 10 of them.
A few, there's 10, there's 20. Yeah, which paper do you want to cite? Right. It's a moving target. So
what happened?
So during each of the four main ones that I'm going to say were, never mind all the little ones, the CO2 level dropped on those too. Yeah. There's a correlation between a ice cap over a continent and a drop in CO2. And I think the reason is simple. The reason is simple is because the CO2 comes from the land. It's from decaying plants and stuff. So, each year, the plants all die and they in the fall and then they decay and that releases CO2. But if that winter an ice cap just came over that, you've just lost a CO2 source. So I think the ice cap itself had something to do by covering the land and preventing the escape of CO2. That it was a synergetic, whatever the word, combined event where not really combined, that's not the right word, but the ice cap itself had something to do with the drop in CO2. And I think that's why we see such a strong correlation there, where when you have the bigger the ice cap gets, the lower the CO2 goes. So the previous three ice ages, and this is again another contention. Well, this ice cap, the Wisconsin actually went further than the, I forget all these names. The ice ages have names to them. And this ice cap was bigger. That was not as bad, but so there is a little bit of circular reasoning to this. In that I say, well, how do I know that this last drop was the largest? Well, because that's when the most of the animals died. Well, why did most of the animals die? Because this was the largest drop. So it's not a fully closed argument. Circularity there, okay? And again, it depends on whose chart you look at. Different ones. I've looked at lots of them for paleo CO2 and paleo this and that and the other. And there's all how many ice ages were there, and so it's a fuzzy picture. We don't.
But the line between the fall of carbon dioxide and the death of megafauna is unclear at this point, and you make it very clear in your piece, which is the fact that it has to do with the success of plant life and the energetics of large animal consumption.
Yes, and very, very specifically because of the types of photosynthesis used by different types of plants.
So this is a biochemical argument. So like if you could summarize it in like I know that you wrote 7 blog posts about this, which are fantastic and everyone should go read them. But in a single sentence.
In a single sentence, when there are 2 types of plants that matter, we'll call them C3, C4. C4 is very recent. It's only been around a few million years, and yet today 39% of the vegetation biomass on land is a C4 plant, like corn and sugar. C3 plants, all the trees are C3 plants, all the trees, and most they are by far the greatest variety. So there's these two types of plants, and this is not one sentence unless you leave the periods out. So what happened was, as the CO2, because there are these two different types of plants, the C4 is much more efficient at pulling CO2 out of the atmosphere, to the point where if you have two of them growing together, the C4 plant, and you drop the CO2, the C4 plant will suck so much carbon dioxide out of the air that the C3 plant will be starved to death. So they're in low CO2, it's the C4 plant is the mortal enemy of the C3. And another thing we know about the Ice Age, it was the time of the greatest extent of C4 plants. Mm-hmm. And what's neat about it is it doesn't matter when it was, but we can tell very exactly what was there in this stratigraphic layer, what type of plant, because these two types take up carbon isotopes in different ratios. And then the animal that eats the plant inherits that carbon ratio. There's carbon 12, which is the main carbon, but there's another stable isotope, carbon 13. There's the unstable carbon 14 used for C14 dating, but that doesn't matter here. It's irrelevant. What matters is these two stable isotopes, of which carbon 12 is by far, 99% of it. But then this, and what happens is the C4 plant will take in more or less, I forget, I think it's more, carbon 13, than whereas a C3 plant will reject it. So the plant itself ends up with this ratio of carbon. And then the animal that eats it ends up with that same ratio in its bones. So you can tell what was the diet of that animal. Did it eat C3 plants, like trees and grapes, and nuts, and things like this? And some grasses, like wheat, which is C3. A lot of grasses are still C3, but a lot of grasses are C4. And if an animal like a bison eats a C4 plant, and you can tell in their bones. So when all the prairies are covered with C4 grasses, and as the carbon dioxide dropped, the range of those C4 prairies expanded out. In Australia, it was almost the entire continent was C4 grass at the worst of the Ice Age. So that does give another to that circular argument. Well, was the worst? That actually adds another. Well, yeah, because that was the greatest range of C4 plants. Why would they have the greatest range? Because the carbon dioxide dropped enough to make them more competitive. They had a competitive advantage over the C3 plant. When you get out along the coast, the C3 plant can still hang on because you're getting air coming in off the ocean that hasn't been robbed of CO2 yet. That's why the interior C4 of a continent, all continents today, and the outer perimeters are lots of C3 plants. You don't see a lot of C3 plants in the interiors of continents to this day.
And to bring this back to the question of megafauna, there is a difference in the kind of caloric intake you can get from grass versus, the examples that you give are wheat and nuts and acorns. And these are very, very calorically dense substances. And so the idea, as far as I can tell, is that there was a shift in the caloric availability on the surface of the earth due to a fall in carbon dioxide, which then caused the death of the megafauna because they were unable to accumulate sufficient caloric input
yes,
in their rangelands, basically.
Yes, in their range. Because as the CO2 drops, both types of plants slow down their growth. Neither one of them is operating optimally. For a C3 plant, it wants 800 ppm or more. C4, it wants 400 ppm. By the way, to take this theory even further, which I did mention in it, is that right now today, we just a massive historic crossing point at 400 ppm, which is where we're at right now, as we speak. We've brought it up from 280 pre-industrial up to 400. Past 400, C3 plants now have the advantage. Isn't that amazing? This is the first time in millions of years that a C3 plant has the advantage over a C4 plant. And what that means is things like corn production are going to flatline. Because once the CO2 goes over 400 ppm, the C4 plant can't take in any more. It's running at its max. It can
All
only.
right, you heard it here, folks. We're getting into like the predictive qualities of this theory. All good scientific theories have to have predictions that they're making. And so, all right, prediction number one: corn will flatline.
Corn will flatline.
All right,
so you call C4s the CO2 vacuum cleaners of the world, basically. My question.
Yeah.
So was that what what were the megafauna eating? C3s or C4s?
Mostly C3. It was big C3 browsers. Except, and I use the giraffe. There are some that still survive. Like all those elephant type animals and the mammoths and stuff. Those you can tell the food in their mouth. Those are these C3 plants. That's what they ate. So anything that ate a C3 plant was at risk.
Mm.
But what's even like the bison? I use that example because there used to be 5 different kinds of bison here in North America. And the biggest ones were gigantic. They're like 2 or 3 times the size of the one that we know. But when the carbon dioxide goes down low enough, the C4 plants are also competing. Because as the wind goes across and a plant takes that CO2, the next plant over isn't going to get as much.
Mm-hmm.
So you think the C4s were eating up all the C3s food, basically?
Yes.
And were the megafauna, what was unique about this last glaciation period that didn't occur previously?
That's a good question.
And that's that tautological question. The CO2 level fell just enough further.
It was like a threshold sort of situation or something.
And we know that it was a threshold because in the 3 previous, there were already events like this happening. It was right on the edge, right on the edge, right on the edge, and then it went over the edge.
I could see that. So and then you kind of make this claim at the very end of your theory that this was sort of from like a Gaian perspective, this is what the planet needed right now as a whole. Can you put that in your own words somehow?
Yeah. Well, looking at all these different events of the history of life on Earth, there's this pattern to it of planning, precognition, planning for the worst, like C4 plants. They came along, the atmosphere was over 800 ppm. There was no reason to have a C4 plant. There was no reason to invent, create, or whatever word you care to use, that type of photosynthesis that had no competitive advantage. So it wasn't survival of the fittest. It was survival of the incompetent.
Abundance for all.
So why did it come around? And yet a few million years later, all of a sudden it was needed because the C3 plants could not. It was not needed. It became competitive. Long after it came into the world, it became very competitive. And finally, it ended up dominating the biomass during the Ice Age. And it's still 40% of all the plants on land are C4 plants still. So and when you say, yeah, we're still in an Ice Age, yeah, we are. And that to me is the key indicator. How much C4 plants are there? Which, by the way, that as an aside, this C4 photosynthesis is a recent discovery, relatively. I don't know exactly, but I think about 30 years or less. So it's not that well known.
So cool. So then the humans come along, right? And we start just cranking carbon into the atmosphere. And the C3 plants are like, thank you.
Yes. I have a list, which is other science article, which I keep meaning to finish and post. And maybe this will inspire me to finish it.
Do it.
The signs for us to look for. I wrote them out as little mnemonic devices. However you pronounce that. It's like Pleistocene. Wall of green. you look at a tree now, like especially in places like Portland or Seattle, where see a tree, the sun, it goes in an arc over the day, and a tree, it puts a leaf out to catch as much sun as it can. And there's some plants that turn it like a solar, they can do that. Most plants can't. So the tree has to arrange its leaves in such a way that it maximizes how much sunlight it can intercept from this moving target during the course of a day. So it has to, put them in different orientations. And of course, a leaf pointing that way isn't going to get when in the morning, and then a leaf pointing, so they're only good for a certain part of the day. So a plant is an extremely intelligent thing in this regard, how it can make its structure in a way that optimizes the solar intercept, how much energy it can pull from the sun. That's the other.
Gets what it needs.
Yeah, it needs water, CO2, and sunlight, and warmth. Those are 4 things, and then vitamins and things like that. But all 4 of those things have to be there, of which water and CO2 are equivalent in as far as their uptake. 1 water molecule, 1 CO2, 1 for 1, right? That's what a plant is built out of, water and CO2 in a 1-to-1 ratio. They're equally important. So anyway, the trees today, you can look in this winter now, but you can look in the summer and their shadow is completely black at different times of day, which means they're putting out so many leaves, they're intercepting all the sun that hits them, regardless of the time of day. And it's hard to research because there's not a lot of data on previous shadow coverage of plants.
I imagine that's hard. That's a hard thing to find in the geologic record.
It is. I've looked in the photographic record, right?
Sure.
Old photos. I don't find trees like this. The trees are bushier, and bushes too. They're much more solid. That's one. I call that blackout, which is the shadow.
That has to at least be partially due to the fact that there have been enormous plant breeding programs that have basically decided what they like aesthetically. Like I didn't really actually know this, but there's this guy whose name I cannot remember right now. It starts with a B, but he's basically Burbank, exactly. Burbank is responsible for like most of the plant varietals that we see around us today that nobody has any idea that this guy was basically the like Frankenstein of plants.
And nobody knows how he did it, even though he said how he did it. You know how he did it? He told us.
Well, it was just mutagenesis, I thought. He just like irradiated. Huh.
No, he said it. I've read him. He said it very explicitly. Like how he invented the spineless cactus.
Which is?
He talked to it.
He talked to it. That's amazing.
He talked to it. He said.
Well, he did also irradiate it.
He told us how he did it. I don't believe he used radiation.
Really?
Yeah, I don't think so. He used hybridization. He talked.
Interesting.
He had it in his greenhouse there in Santa Barbara or wherever, and he'd come along every day, and he'd pet it, and pull some of the spines off, and he'd say, there, you're safe here. You don't need these. I love you. I'll take care of you. Whoa. And he wrote that in, and he meant it, and he did it for other things too. Huh?
I've been trying that with a houseplant that I have very nearly murdered, and it has not been working. So this is an N of 1.
A lifetime of abuse, maybe it takes.
You're not Luther Burbank, okay?
No, I'm not.
So, now, I'm not saying it's true that that's how he did it. I'm saying that's how he said he did it.
Sure, yeah.
And
okay, but
the other thing, nobody's been able to replicate him. It was like this shooting star that came and went and never again seen.
You see this occasionally in science. Like there's this thing in laboratory experimental science that you find people that are said to have good hands, quote unquote. And this is such a common thing where you find someone who is capable of doing a technique or accomplishing something, and even though they write it all down and it's in their lab notebooks and they tell you how to do it, somebody else comes along and tries to do the same thing, and they don't have that combination of monastic devotion and intuition and technical ability that these people are, 1 in a million.
It's the antimorphic field.
Well, it's really interesting. So we recently watched a documentary on the way that electromagnetic waves affect water.
Yeah.
And so it was basically this video. Luc Montagnier, who's this French Nobel Prize winner for HIV.
Okay.
He's now running a lab where he basically believes in the memory of water, where you can take you can put a DNA molecule into water, allow it to affect the water molecules, make a recording of that electromagnetic effect, send it to a different laboratory, and
also known as a CD.
Also known as a CD.
Audio wave
exactly.
file.
They send like a wave file to a different laboratory.
Yeah.
And then that laboratory is supposedly able to reconstruct the DNA molecule from a tube of water.
And this is
like
homeopathy. This is
homeopathy.
the homeopathy, and it's Rupert Sheldrake's morphic field.
Unfortunately, that is the only lab in the universe that can do that effect. And
Not
only
only-
one gentleman, the technician in that lab, is the only man. Even if everybody follows this protocol, they can't do it.
Okay.
So,
so
make of it what you will.
Right?
I know these are mysteries, and we don't have all the answers to everything. Never will. But we want to look at this and ask the question openly, without just being, "Oh, you're a conspiracy theorist," or you
Right on.
spooks in the woodwork and whatever.
Yeah, there's all kinds of weird stuff. But so
I'm just a tourist. I'm going along and go, "Wow, look at that! Look at that! Look at that!"
Okay, so you look into the record and you're like, okay, so plants and trees and bushes are more verdant now than they were. And so one possible explanation is that they've been bred to be so. Another possible explanation is the fact that the increase in carbon dioxide is helping them be bushier. And I am inclined to agree with you on that, because there has been evidence of the fact that tree cover around the world is actually increasing.
Massively. That's from satellite data.
Right? And
one estimate, it's like 73% since the start of the Industrial Revolution. And all they're doing is measuring leaf coverage, what we were just talking about with the intercept. They're measuring the leaf coverage from space. And that's a pretty clean data set.
I mean, hydroponic produce growers blow carbon dioxide on their plants to make them bushier. I think it's pretty well determined.
It's
sure.
It works.
Very well known. Yeah. Very well known that it's essential. So, but yeah, the satellite leaf coverage. So these other signs are the increase in growth rates of trees. Another one I call exploding stumps, which is like here in the Northwest, we have these big leaf maple. You cut the stump, and it used to be when I was a kid, you cut a stump on a maple tree, that's it, bye, done. But now these suckers explode out of that. That's why I call it exploding stumps. But like bamboo level rates of growth. Red alder is another one. These trees are growing taller faster, and they're I've seen growth rings like this. Okay, like this, like on a redwood here in Seattle. There in Seattle, I mean, not in Seattle. All right, I mean, just massive rates of growth. That you look at the old growth wood, and the grain is very tight. For year to year.
Yeah, like if you go to the Muir Woods, they have that slice of the tree, and like somewhere in the tree is like the year Jesus is born, and then I think it goes like all the way back to like ancient Roman times. But those are very, very thin, like pencil thin rings. So you're saying that in redwoods that are recent cuts, you see larger growth rings?
In all species.
Interesting.
I've seen poplar trees 2 feet around the base, and I go around and count the rings, and they're like 15 years old, 70 feet tall.
Yeah, it's really interesting. We were talking about dating methods earlier, and I came across the notion the other day that they actually use tree rings in succession to date back something like 10,000 years into the past. Like we were saying, like, when did this actually happen? Well, they'll like take a tree, they'll line up the rings from it to like its earlier generation, and then they'll do this all the way back to these like ancient timbers that they find in these old digs. And
yes, but it's dendrochronology, and you are not allowed to have access to that data to check their results.
Me? Not even me?
Not even.
Not even Dr. Hot Eyes?
Well, we'll have to look into that.
Which is already a massive red flag. That's one. Two, that's a red flag because we can't verify that claim. Two, there's what's called floaters, which are sequences in the data. Like if you have a log that's got 300 rings in it, you've got a sequence, but then you don't have the one before, you don't have the one after. So it's floating in time. It tells you the climate of those 300 years, but where were those 300? When were those 300?
So there's missing links.
So there's missing links. Yes, that's a better word for it. There's missing links. There's a thing called the Roman gap, which is about 1,000 years worth of missing link.
Huh.
Really?
I didn't know that.
Yeah.
Write that down for later.
Yeah, we got to look into this. We're working on a movie about missing time in geologic history right now.
You're preaching to the choir. I study these things too. Yeah. So yeah, the 80 chronology is a little sketchy. And if you ever go to,
I mean, these are best guesses, right? Like people.
Yeah. And they like cross correlate them with other methods, right? Like that's the defensibility of some of this dating. At least in the recent past, is they're like, well, we'll do like 20 different methods, and they kind of agree. And
there's it's one thing to say, oh yes, it's our best guesses, and we're all jolly good fellows. It's another thing to hide the data.
Well, this is true.
Yeah.
I mean, like access to data
problem.
is a huge problem, and this is like one of the biggest places where science is really going through a hard reckoning, right? Because it's like I saw an article today about the fact that some pediatric brain tumor study had to retract the results because of the fact that the way that they had treated the data was not robust. It's like, it's just a constant thing that people are constantly finding that they're like, well, we did some statistical stuff here and some statistical stuff there. Like, we're trying to interview this woman who studies the microbiome, and she's a philosopher of science. And it was really interesting because we had a pre-show meeting with her, and she was basically like, look, the microbiome studies are not as robust as you think they are. And we were both kind of just like, what are you talking about? That's not possible. And then she sent us all of these papers, and it's just paper after paper after paper that has made conclusions about links between microbiome and obesity, autism, depression,
results.
And it's like,
well, not only that, but they're just like, overhandling their statistical analyses. And I mean, a very common mistake that was found in a bunch of papers was that they would transplant fecal matter from humans into these immune deficient mice, and then they would basically count each one of those mice as a replicate in the experiment, but in reality they'd only used one donor from a human, or like two donors, right? So the real replicate size should be like 2, and so like all the effects basically vanish.
Biologists, not statisticians, not good math people, generally.
The third problem, there was the floater, the missing link problem. I forgot what the first problem was. Oh, the missing data problem. Yeah, and the third.
How to get it?
Huh?
Yeah, like how to get a hold of the data.
You can't get the data. And the third problem is, and this is more to do with just the vagaries of the way plants grow. Is you can have this log, and that tells you what the climate was where that tree lived, and its immediate environs, but it doesn't tell you about the next valley over. And so what they get these different logs and timbers and things like this, and tree logs and whatever, and from different places, and then they're trying to correlate the ring sequences between the different trees, and now it gets into statistical massaging. There's a degree of subjectivity into how you match these two different ring sequences. Do they really match here? Okay.
If you really want them to match, maybe they do. How bad do you want it?
Yeah. So it has that.
When's that next grant cycle?
Yeah. So it's also all these dating techniques we have. They all have this.
Deep time is hard. Deep time is really hard, right? Like, and when you start to look into ice cores and you start to look into rock cores.
Those.
It gets really difficult to be able to say something robust. And when you start exploring how do they come to say the things that they say, it becomes, you basically have to get a master's level or a PhD level understanding and read a tremendous amount in order to be able to understand the rationale behind the methods that they use, which is why it's difficult to have a conversation about, hey, is this a good method or is this not a good method? Because who outside of the field has the time to be able to really explore, understand, and then critique the approaches that are being used? And that's just baked into all of science at this point. It's very, very hard to evaluate super complex methods that have been built, like the data for a lot of this stuff that established the methods was collected in the 50s and 60s. There was this golden age, an explosion of methods, radiometric dating, probably dendrochronology, like all of these techniques that were used to be able to say stuff about the natural world had this moment of blossoming. And now they're kind of, they're accepted, and what are you going to... And so challenging them is difficult because of the nature of institutions, right? Like if you're...
They're all like sort of they're all built in support of one another too. It's difficult because the biggest argument that they have in their favor is that, hey, we all agree, all these methods agree with one another. But of course, like they're incentivized for them to all agree in the first place. And like, there's a lot of relative comparisons where you have like a known age sample, which is compared to these. And it's like, well, how do you know that age sample? And they're like, well, we use this other known thing. And it's like, it just gets into...
It's a circular argument.
But we're going to get to the bottom of it. We're going to do like a serious movie on radiometric dating and all these... We're going to get there. We're actually meeting with a geologist after we get off the phone with you at this dude at Cornell who teaches radiometric dating. Yeah. So we're going to pick his brain, and we're not going to stop till we make sense of this. So
yeah,
we'll come back to that later.
Yeah, C14 is... There's all... I'm sure you've read some of the problems with that.
Well, they just updated it. They just added 5,000 years onto all C14 data, from what I can tell. There was like a Nature paper that came out last year, 2 years ago. So it's on the move.
And next year they'll subtract another 10, and it's a moving target. But it has to be, because
it has to be.
Yeah, we don't know.
So
okay, well,
to continue, exactly. So we basically have this wall of green.
Back to the predictive features and why it's important to understand these things.
Because corn's going to slow down, trees are going to get bigger.
Matters. Yeah, future matters, right? And you want to show up for that. So what's it going to be like? Yeah, the ecosystem shifts. All over the world due to that relative competitive advantage between C3 and C4 plants, and now the accelerated growth of C3 plants. C4 plants are all of the C4 plants. Remember that's not just corn. That's 40% of the entire biomass on Earth. Land is now running at its maximum limit. It cannot increase any further beyond that. Because but
the C3s can. You think they can sort of... Yeah, so they're going to just take all the sun space, basically, and then nothing to eat for the little guys on the ground, basically. Well, they're not so little back then.
That's another thing that's happening, the dark cave. Like when you have the tree canopy gets so dark that it becomes like a cave underneath. That's a shift in the ecosystem, where before the sunlight, more of it could get to the forest floor when you have a closed forest canopy. And nowadays, just looking along the freeways here, and you see these evergreens that are not very old. They're like 30 years old, and they're so interlocked and intertwined that it's just a cave underneath them.
Yeah, there's actually places around here where you go out and they're like, you can see the little oaks like underneath, like kind of dying off. You know what I'm talking about?
Well, yeah, it's a transitional ecosystem. Like as the canopy closes. And it depends on what kind of forest you're in, right? So like the Russians have a saying, and I might get this wrong, but a redwood forest is a forest that you pray in. A pine forest is a forest that you celebrate in. And a fir forest is a forest that you hang yourself in.
That sounds really, really Russian.
Freaking Russians, man. Brutal. And then we drink.
You drink before you hang yourself, I think. But that's to say that like it gets dark. These like evergreen forests that are along the roads, they're mostly fir plantations. They're Douglas fir, they're noble fir. And those things...
I'm old enough to remember. I'm old. the forest before when I was, in the 60s in Portland. It wasn't like that. That's what I mean. We need the old photographs because, it was dark under the trees, but it wasn't like pitch black. All right. Like the Tillamook burn. Are you guys from Portland?
We were there for a while.
Yeah. The Tillamook burn, all the trees burn, and these new ones grew up just like they do now, but it never got so dark. So, and again, back to the satellite data is pretty objective stuff, right?
Right. So the canopies are.
You just got a meter that's bouncing out reading the infrared off of that, and with the leaf coverage is increased. That one we can start right there because that's agreed to by mainstream.
And this is all like part of like a feedback cycle in your conception. It's like at some point, like it's sort of in this weird balance, but then it's just like once it goes past some threshold, the C3s just take over, they squash out all the C4s, and then the big animals are just like, what's for breakfast? And there's nothing, right? Something like that.
Yeah, not quite that drastic.
Okay.
I mean, you're taking it to the limit. But if you look at the growth rate charts of the two types of plants, it's very interesting. I'll try to do it. Let's see. I would go like this. Does that look right for your graph?
Mm-hmm.
Okay. The C4 plant at zero CO2, nothing can live. No plants can survive. But at only 20 ppm, C4 plants there's enough molecules that they can sift them out from all the other ones and use them to build their structure.
They're very efficient.
Super efficient. Incredibly, they could suck a gas out of the atmosphere to that down to 20 ppm.
Got it.
Yeah, but and as you raise the ppm level, that's what this is. The horizontal is raise the ppm level from 0 to a high number. So at 20, C4 plant starts to grow, and when you get up to 400 ppm, that curve it flattens out, dead flat. It just goes up, and then flat lines at 400 ppm, which is where we are right now. That's why.
So the C3s are totally happy with that level, but they're
it goes like this. It probably has a flat line up there somewhere, but I don't even know where it is. It just keeps going up. So when at 400 ppm, where the C4 flat lines, C3 just as you increase carbon, it just keeps growing faster and faster and faster. Whereas C4, that's a maximum growth rate. It stops. It can't grow any faster.
And the big animals were eating the C4s? Am I correct?
Some of the big animals, most of the ones that died were C3. They were eating.
Then I'm totally confused.
So C4 is grassland. C4 is the stuff that's on the ground.
Yeah.
And so you have and Forrest, make sure that I'm retelling this correctly, that I'm recapitulating this. So you have a historical decrease in CO2 levels, right?
During these glaciations.
And so you get to a point where CO2 falls to a critical point, and the big plants, the C3s, can no longer grow. Like look at this graph that's right in front of us, right? And what proliferates is the C4 plants, the grasslands. And that's the condition that we're in right now, where you have a large majority of grasslands that do not support large animals. Periods. But we're glacial period or not.
But they died right after the glacial period.
Yes, the large animals.
Yeah.
Okay. Yeah. So that's because the vast majority, and this is what Forrest was saying, is that the vast majority of the flora at the time of the glaciation was these C4 plants. And that partially makes sense because if you have a decrease in precipitation, what you're going to grow is you're going to grow grassland because you have to have a 1-for-1 carbon dioxide water relationship. So even if you have carbon dioxide but you don't have water, you can't run photosynthesis efficiently. And so these plants that are down close to the ground that don't need as much water and are more efficient at taking carbon dioxide out of the air proliferate, but they don't have as many calories in them. You don't get nuts. You don't get fruits.
So the glacial periods were really hard on the big animals.
Yes.
That's fine, but there was lots of glacial periods that weren't hard on them.
There was a corresponding decrease in carbon dioxide fall during this last glacial period. That's the point. It's not the glaciation. It's the fall in carbon dioxide. Is that correct, Forrest?
You beautifully put. Everything you said.
It doesn't seem to be much lower than the rest of them.
And the thing that Shiloh is reacting to is the fact that we've pulled up this composite CO2 record for the last 800,000 years. And if you look at the composite CO2 record for the last 800,000 years, the level of carbon dioxide, the decrease in carbon dioxide levels at the end of the last glaciation does not appear to be significantly lower than any other time prior.
Than the previous three, the 180 ppm.
Yeah, so it goes down to 180 basically 800,000 years ago, 700,000 years ago, and then it stays it stays maybe around let's say like
This is 100,000 years
200.
ago.
Yeah.
This is the most recent one.
Yeah, so like it definitely dips down to like 190, but it's been there below
10
before.
times in the last million years.
That's what he's trying to say.
According to that graph that you pulled up.
Which is ice core samples from the last 800,000 years. Do you have a different set of data that shows that it hasn't?
Different ones. Yeah. This again is another fuzzy area where there's lots of these charts. I've looked at lots of these charts. I've also looked at how the ice core data is theorized. When you say, oh, there's these massive data sets and they all agree, I always look at the core assumptions first of the theory. Okay, you assume that all the trees in an area all had the same growth rings, and all the carbon-14 decays at the same rate. The core assumptions underneath the theory, the beginning, start there. Well, for the ice cores, that 800,000 number is extremely suspect because for numerous reasons, which I won't go into here, but because I don't know how much longer you can go. But that's another dating method that's very, very shaky.
Well, so the question, I think that we have to ask whether or not we can accept. There's an axiomatic assumption of this theory, and the axiomatic assumption is the fact that the ice core data, or not the ice core data, that the carbon dioxide dipped lower during the last ice age than it had previously,
or that it was a cumulative effect. Because what is apparent from the data is that the carbon dioxide levels were they weren't spiking as high in the early part of that million-year period. And so there was some sort of cumulative effect going on that there was a triggering point.
Right, so
there was a switch between the C3s and the C... Is the switch between the C3s and the C4s, is that important in your theory?
Absolutely.
Okay, so there's a switch that kicks over.
Yeah.
And that's the sort of feedback event that I would expect if you have some massive extinction or something, that there's a switch in the conditions that happens because it's very finely balanced, and at some point it just leans in the other way. So what's going on there? Like, you're saying that the big animals were eating mostly the C3s, but the C3s
they're the high CO2
are very
condition.
Unhappy in the basically in the glacial periods.
Yeah.
Okay. And so there was basically this kickover. There was no C3s for a while. And what's going on right now, though? You're saying that the C3s, what's going on in this day and age? What's up with the humans? How are we involved in this?
All right. We'll get to the humans in a minute. I'm going to finish this thought that of the ecosystem shift. That's what's going on. We're retracing the steps that led to the ice age. We're going back the other way, and all the climatologists would agree with that statement, that we're already back to Pliocene, which is the era before the Pleistocene. We're already back at 400 ppm. We're back to that level. We've risen above. And what is happening, and this is, all those billions they put into studying global warming could put just a little into like, what's going to happen to all these ecosystems? And it's not necessarily all good news. When the competitiveness between the different types of plants is shifting rapidly, very rapidly, okay? And like, I think right now, if you went out and just as an experiment, seeded an area in Kansas that's all prairie grass or cornfield and seeded it with trees, they would grow and you would have a forest in the middle of Kansas where you couldn't have 50 years ago.
That would be an interesting experiment to plan. So if anyone listening has a plot of land in Kansas, reach out to us. We have some ideas for you.
And you did say something, and you can think of it very on a first pass. Tree equals C3, grass equals C4. All right, trees and grass. That's the first iteration, the first order of what we're talking about. Okay, even though wheat is a C3 plant. And there is one C4 tree that's just this stubby little funny tree that grows in Hawaii. It's on the grand scale, it's cute, but it's worthless. So basically, trees are C3s, grasses are C4s, right? Most grass, not most, yeah, well, by mass, most grasses, but there are still C3 grasses. But that's
Okay.
a simple way to think of it, okay? So starting with that, it's, okay, as CO2 drops, grassland expands, forest decreases. As CO2 rises, grassland contracts, forest increases. The crossover point where they're even Steven competitors on the same playing field with the energy, actually it is around 400. It's actually a little less than that because a C4 plant needs more energy to run its kind of photosynthesis. It needs more sunlight than a C4, than a C3. It's actually less efficient, energy efficient. Okay, so but it's around where we are right now. Is this crossover where the forest land has a competitive? Oh, another thing we're seeing is arboreal reconquista. That's another one of those. I mentioned blackout and wall of green. Wall of green is all the plants fill in, and you can't see through them. One layer of trees or bushes, you cannot see through it. It's like a brick wall now these days. Arboreal reconquista is massive. What's happening in the American Southwest, out in the prairie, what do you call that, scrubland, is we're seeing bushes popping up on the rangelands with the farmers, the ranchers. And for them, it's a nuisance to have all these bushes just popping up out of nowhere. Okay. In Idaho, the forest, the trees are taking over the elk grazing land to such an extreme that the state is going out and cutting them down. And it's in Wisconsin. So you see, we're witnessing this in our lives happening. This arboreal reconquista. The trees are taking over the grasslands. So we're seeing that shift right now. And again, you think the elk, perfect example. Apparently, they don't like to live in the forest, I guess. Grasslands. I don't know much about elk, but the problem has become so extreme that they're literally cutting down trees over there just to make more room for elk hunters and elk.
But the giant elk, on the other hand, or the giant elephants or something, would have loved the trees. Is that the idea?
I don't know. Like the Irish giant elk or giant deer is called a giant elk too. It was enormous, again, bigger than a moose, and had a range across Eurasia. It's a huge range. But I don't actually know what their diet was. There's just I haven't researched every last animal here. I actually know what those animals ate. But yeah, I think those are more of a forest animal. But for some reason, Idaho, the elk they have there's a big push to stop their range from contracting.
I mean, the question of what the animals ate. So, the question of what the giant animals ate is pretty relevant, because if the giant animals were eating mostly grasses, then it becomes the theory becomes less tenable. But this is no, I mean, like, because if they prefer the grasses and the grasses are the most abundant, then you wouldn't expect the megafauna to collapse with the abundance of grasses. You would expect them to flourish. And so well, so if you expect the megafauna to flourish on a grassy planet, then it's a harder story to tell why the megafauna go extinct on a planet that's grassy. Because their food source is most abundant. And so you would expect them to flourish times 10 on a planet that has way more grasses. And so the question of what is it that they ate is relevant for that, but that's something that, can be reconstructed off of whatever they find in their stomachs, etc. Like, I know that you mentioned in the
we're ultimately trying to say why they died, right?
The carbon ratio.
Yeah, the carbon ratio. And the carbon ratio depends on their
food,
diet.
Right?
And so their diet has to be arboreal rather than grassland in order for the decrease in carbon to cause their extinction. Which might be the case. I don't know. I don't know what these animals are eating. And this is something that we do know. Okay.
Pretty close from their carbon ratios. And that's one thing.
Oh, that's right. That's what you were saying, is the fact that the bones of the carbon ratio have different C4 versus C. Got it.
Different C12 versus C13.
Got it.
You can tell what that animal ate. And I did go around to a few hundred different types of animals and look at what they ate.
Fascinating.
Right. Yeah.
Okay.
Were they C3 browsers, C
Mm-hmm.
grazers, or C4 grazers? There are no C4 browsers because there are no C4 trees.
Mm-hmm. And so I guess is there a type of C3 grass that also was replaced? Like because it seems like I wonder if there was a lot of I don't know enough about the past to know if there was like abundant wheat, but wheat is very calorific.
I'm trying to figure out what these big animals ate. Sorry,
The bison were definite. Those are like holotype or archetypical C4 grazer,
Mm.
almost exclusively. That's what
Mm-hmm.
they eat dudes. They still around.
Right.
Yeah, those are C4 grazers.
Got it.
And
Okay.
look at the way they're built. They're built
Like tanks.
but yeah, like tanks, but they have to hunch down like this.
Hmm.
So you know they can't browse because they can't raise their head. They're only eating short little plants. That's why they're shaped like that.
Right.
I just found that the giant elks lived in the woodland environments. So
I thought so, yeah. So I don't know why they have to cut all the trees down for these other elk.
Well, they're a different kind of elk. They're much right. The giant elk might have had a different niche than these elk because you would expect that there is a differential in the ability to survive, right?
We've seen the National Geographic with all these giant elk herds going across the prairie.
Right. Yeah.
This thing you're calling a giant elk, it's actually a deer.
Well, it's just a less giant elk, right? Because these things were, I mean,
the Irish giant elk is also called the Irish giant deer. Like they can't figure out.
And well, we've gotten into this.
We know deer like Bambi. I mean, I've seen Bambi.
Yeah, exactly. That's a small one. But I don't know that Disney was ecologically consistent, but I'll allow it.
Well, didn't Bambi live in the forest?
I think it did, yeah. And I see deer in the forest.
Bambi
here.
like the meadows. Come on. Bambi seems like a meadows kind of guy.
Maybe that's the difference between a deer and an elk. A deer lives in the forest, elk lives in the grass.
Yeah, maybe. Well, so this is actually interesting because the question of speciation, right? So it's like, how do we know that the Irish elk was a different species than the current elk, rather than just like a type of elk that was
and like what
larger?
the hell is a species, anyways?
Oh, let's not
do that. Let's not do that.
I mean, all these fuzzy questions, and I keep looking at the picture of the dots and trying to connect them.
Well, so what's the human? What are the humans doing here, man? What's going on?
This is the capstone of the theory.
Yeah, this is the shining gem at the top of the pyramid.
So we have.
It's called the eye.
Simplified model. We have these 4 ice ages over the past million years. In the first 3, we were losing animals here, just a few, but then we had this massive. Okay, there's 3 ice ages. And we lost a few animals here. We lost a few there. We lost a few there. In the meantime, there was these proto-hominid critters running around at the same time. And then, and that second to last one was about roughly 100 and something thousand years ago. Roughly about the time on the mainstream timeline that good old us showed up on the scene. Right around that second to last ice age. And then on this last ice age, pow! All the factors came together to cause this extinction event, and leaving us standing. So, if you look at that progression, it's almost, and then darn near catastrophe. And I put a question in there near the very end. Another mystery about this is. The CO2 level dropped and the other conditions of the ice cap, the climate, to cause this massive extinction. Why did the CO2 level only drop to 180? Why not go on down to 140 or 100 or 20? Why did it stop there? That's very mysterious. Because if it had gone down just a little bit further, according to the CO2 extinction theory, whatever you want to call this, there wouldn't be any more horses and giraffes and elephants, any C3 browser, cows. I think no, cows can eat C4. Any animal that has a No, I take that back. But I'm pretty sure cows can eat C3 and C4. I'm not positive.
Well, I know that cows eat oak seedlings. Well, yeah. So like your question was before you got off the rails. Why doesn't
go lower? And furthermore, in the very next ice age, which is going to start whenever it feels like it, will it go lower? The very next one, the one that's in the future, right? Will it go below 180 and take out at least all that kind of life? How far? And if it does go, how much further lower? And we don't know, because we don't know where all the CO2 comes from. We know that it goes away. It's continuously having to be pulled out of the earth, and then it mostly it either gets buried as sedimentary rock, or it drops to the bottom of the ocean floor as ocean sediments. So the carbon is continuously falling out of the biosphere. So it has to be continuously replaced. It's a dynamic system. It's not a fixed thing, and it's constantly having to be renewed. And it's been constantly running out. And if something isn't done real soon, it's going to continue running out until there's no life left on the land. And if all the carbon dioxide in the ocean goes away, which would take a lot longer, then there wouldn't be any life in the ocean. We'd be dead, gone.
So your theory sort of culminates in the idea that the humans have essentially evolved in order to do the job of putting this carbon back up in the air.
That claim is put forward.
You shouldn't hide from it. It's interesting. It's really interesting. It's kind of buried here, but
it fits in the rest of the picture of this idea of pre-planning. Why do these things come along, like C4 and all the different creatures, and this then I mentioned those types of invention of the first kind, second kind, third kind. First kind is the creature just appears in the record, fossil record, out of nowhere. No answer, just boom, there it is, right? Ex nihilo, out of nowhere. And inventions of second kind, which is the joining together of two organisms. Then there's inventions of third kind, which is the morphic field again, really. I did point to I waved at Sheldrake there. And that's what C4 is. Because this C4 process, it didn't radiate out in a tree of life, and it started with one little grass stem, and then it made these other ones, and descendants and ancestors. And it didn't do that at all. What happened was, it was worldwide. A bunch of different C3 grasses all of a sudden learned how to do C4. There was no biological link between these two different species that ended up having the same structural. It's a complicated structure. You can't just evolve it from a molecule. It's complicated.
And that's kind of like, I think what you mean by this morphic resonance thing, and just this idea that the strategies converge across different but related and similar ecosystems. Like, we like to play with the idea of whether there's monkeys like us on other planets. Yeah. I personally kind of lean towards probably, yeah, exactly, like monkeys happen all the time. Maybe even in the deep history of the Earth, like the most popular theory is that the monkeys evolved on the same continent, not us, I'm just talking about monkeys in general, and then they spread out or whatever, or they somehow swam across the ocean because it was closer together or something. They ended up in South America. But it's also, we like to toy with the idea, and we had this multicellular evolutionary biologist on the show the other day, and we're like, well, they could have just evolved this separately. Like, DNA might just be the most stable conformation of these it might be just the way life is done. It might be that C3 to C4 adaptation is just the most efficient thing to happen, and everybody figured it out at the same time because it's the only way things could have gone.
Based off of the actual physical shape of the molecules that are involved. And that's kind of a hard thing to consider, where we have this linear track of evolution, but it could be that evolution just kind of ratchets over based off of changing conditions in a way that is not. You talked about dendrochronology being difficult because it's like valley to valley travel of how do you take a timber from this valley and compare it to a timber to this valley. But if global CO2 levels have changed to a degree that suddenly there's a need for a different approach, then you would expect it to happen like ratchet click, as opposed to a bunch of different approaches that are suddenly tried. Like maybe the step isn't as far as we think it is too.
So yeah, it's mysterious. We don't really know. So we don't.
It's a hard thing to talk about too.
We don't,
Right.
and they don't know. And anybody says they know, they don't know.
Well, we got stories, right? And like to take it back to the beginning, you know, science is really just a series of stories we tell ourselves. We add those little dots on the map and we try to connect them better every time.
Yeah.
But Forrest, I feel like we have been talking to you for a while about this, and honestly, you do so much other cool stuff too. I feel like we should catch up again soon and get deeper into it. You're doing these. You got some cool engineering projects. You got these Bishop cube things?
Yeah, that's a shape-shifting machine.
Shape-shifting machines. I mean, oh man, like we need to get back together.
Okay.
But I think we should wrap this down for today.
Yeah.
This is a lot to digest.
You want a final thought?
Yes.
Oh yeah.
Yeah.
Closing thoughts with Forrest Bishop.
Closing thought is that the reason this, whether or not the theories of the morphic field and the pre-planning that looks like it occurred, and the experimentation in the Cambrian and all that, we know that the ecosystem is changing, right, as in our lifetimes and in the future. It's shifting. It's becoming more congenial for trees and less for grass. And this is going to be a mass, and for food production like corn. It's massive changes we're right on the cusp of. Ecological changes that are absolutely off the radar screens. I think people in like forestry and some farmers know about these things, but it's not on the radar, and it's not in its proper place about what happens when trees can outcompete grass, and then all the animals and the whole ecosystem that comes along with that. What happens to that area? What about if you're a real estate developer? Well, I'm gonna put this city here in Kansas, even though there's no trees, because there's going to be. There's across a lot of industries and just your life in general, your backyard. It's important to understand what this rising CO2 does to shift the ecosystem. So for that reason alone, it's important to follow these things, to learn more about them. For everybody.
And then the next question is, how does the ecosystem feed back to affect the glaciation periods, or what the heck is going on with that? Because it's also, I mean, the reason this even happens in the first place is poorly understood too.
We don't even know why the ice ages happened.
Right. Well, there's theories.
Yeah.
There's some theories. There's some books. There's some textbooks.
Sure.
There's some concretized theories even.
Some peer-reviewed theories and some not peer-reviewed theories. There's the world is full of them. But I think that's a beautiful place to close. I mean, the interplay between the world that we live in and the way that we occupy it and the way that we wish it to be versus the way that it is the sort of the central challenge of the human industrial society, right?
But this is good news.
It is, maybe, because there is a huge push to treat carbon dioxide as being a molecule that needs to be removed from the environment as much as humanly possible.
And we need water as well, because they're equally important.
But I mean, I think that the reimagination of the story of the planet that you put forth in the Pleistocene Murders is a really beautiful one, because it gives us a perspective from which we can look at the industrial decisions that the species makes and begin to question the larger impacts that we make, whether or not there are some good things about the industry of the humans that go hand in hand with the challenges. And maybe it can even help people start to think about not CO2 as the one molecule that needs to be removed, but start thinking about all of the other stuff, the stuff that messes with hormones, the stuff that messes with reproduction, the stuff that's made testosterone fall by 20, 30% over the course of the last few decades. Like, There are huge, huge problems from industrial society that have nothing to do with CO2. And if your theory is correct, the CO2 would actually be a net gain because we'd be able to support more human beings on the planet under a higher CO2.
And more trees.
Well, more trees, more
And people
more,
love trees.
more calories, right?
Yeah.
So it's like, this is, it sits at the intersection of so many things. And and so I just want to say thank you for coming by to tell us about it and to sort of to lay it all out for us and to let us, pull on all the threads. So thank you.
Yeah, it's been really fun to talk to you.
Very welcome. Thanks for having me on.
All right.
My pleasure.
See you later, Forrest.
Bye.